Hi Algebra 2, this is Mrs. Langford. We're going to continue with the notes in section 4, adding and subtracting rational expressions. But we're going to do an example of rewriting rational functions. Now we did this in an earlier section when we used long division with the rational. So we're going to use a different method, and it's kind of interesting. It's not a big focus, but I do want to show you a few examples, and then I gave you a couple of problems on your homework. So in this example, we're going to use a method that's called inspection. So basically, what you do with inspection is you look at the rational and you compare the numerator with the denominator. Now remember, the form we're trying to get it in is, if you're in third hour, it's Helen Keller form, or if you're in seventh hour, it's Downsy-Exy form. So we're going from this first form to this second form. So if you look at the numerator and denominator, one way is if we try to rearrange the numerator so that we have an expression of x plus 1. So we could rewrite 3x plus 5 as 3x plus 3 and then plus 2. Now the reason why I did that is because then I see that I can group together my 3x plus 3 and I can factor out of 3. And that'll give me 3 times x plus 1 plus 2 all over x plus 1. Now that seems a little random and strange, but here's what we can do with that. Now we can take that numerator, or I'm sorry, the denominator, and we can split up the numerator with that denominator. So we can do 3 times x plus 1 over x plus 1, and then we can split up plus 2 over, oh here I said 1 and I wrote 2. 2 over x plus 1. Now I bet you can see what we're getting at. In the first expression, we can divide out the x plus 1 expressions, and we'll have g of x equals 3 plus 2 over x plus 1. The only thing left to do is just to rearrange that. Now the directions say graph the function, but we're not going to graph the function. And I'm not going to have you describe the transformation, although I know you could. You could say that the graph is shifting 1 to the left because of the h value and 3 up. I just simply wanted to expose you to this method of inspection. So let's look at another example. So we're going to rewrite g of x, which is 2x minus 4, over 2 over x minus 3 in that form. So I'm inspecting and I'm comparing my numerator with my denominator. I want to try to do something with the numerator so that I can factor a little and end up with x minus 3. So I noticed I have a 2 in front. If I had a minus 6 down here, I could divide it by 2, factor out that 2, and have a minus 3. So here's a little technique that you can do. You can add and subtract a value that you want. So I would like a negative 6 to be there. So I'm going to subtract 2 and add 2. Essentially what I'm doing is I'm adding nothing to that, but I'm just doing it in the form of negative 2 plus 2. Now what I can do is rearrange the numbers in the top so that I can combine that negative 4 and negative 2 to get negative 6. And then I'll just have my plus 2 at the end. So my first two terms in the numerator I can group together and I can factor out of 2. I will still have that plus 2 all divided by x minus 3. But now I can split up the numerator with that denominator. So I'll have 2 times x minus 3 all over x minus 3 plus 2 over x minus 3. Now a few more steps of simplifying, so dividing out the x minus 3 and then just changing the order will get us in the correct form. So we'll end up with 2 over x minus 3 plus 2. So the takeaway on this problem is this technique of looking for a value, inspecting, I guess, that's why this is called inspection, looking for a value that you could have in the numerator that will allow you to factor so that you have a match between a term in your numerator and your denominator. So you can add and subtract the same value, and essentially, oh sorry, that's my dog, essentially you're adding 0 to that numerator, but it just is has a different look to it. And then you can manipulate those numbers to rearrange that equation. All right, let's try this next one. So g of x equals 8x over x plus 13. And remember, the form that we're going for is g of x equals a over x minus h plus k. So this next technique, it's related to the one that we just looked at. It might blow your mind a little bit. Okay, so I need to do something up top so that I can match this expression in the denominator, x plus 13. So I know I'm going to need to factor out that 8. If I had a value, oh, let's try that again, okay? If I had a value added to my x, that when I divided it by 8, I got 13, I would be set. So over here in my workspace, I'm just going to figure out what 13 times 8 is, which is 104. So if I add and subtract 104 to my numerator, again, I'm basically adding nothing, just in that form. Then I can group these first two terms together, factor out an 8. 104 divided by 8, we know, is 13. Now I've got matching expressions. So then I can divide that denominator between these two terms. So 8 times x plus 13 over x plus 13 minus 104 over x plus 13. So now I'll divide out my x plus 13s and then write my final function. So the term on the right I'm going to list first. So it'll be a negative 104 over x plus 13 and then plus 8. Now let's move on to another type of problem in this section. So this is complex fractions, and it's kind of on the theme of common denominators and least common multiples. A complex fraction is a fraction within a fraction. So it is a fraction that contains a fraction. So it's not just a difficult fraction, not just complex. It actually is a term that means you'll see a fraction within a fraction. There's two methods to simplify these. So the first method is you simplify the numerator and the denominator by writing each as a single fraction. And then, since it becomes one fraction divided by another, you do the keep, change, flip method. So you multiply the numerator by the reciprocal. of the denominator. Now, method 2 is slick. I must admit, it's my favorite method. I'm going to do both of them a couple times so that you can see them in action. You're going to multiply the numerator and the denominator of this complex fraction by the least common denominator, or least common multiple, of every fraction that you see in the problem, and then you'll simplify. So, example 6. 5 over x plus 4 divided by 1 over x plus 4 plus 2x. So right away you can see that you have fractions within one larger fraction. So this qualifies as a complex fraction. We're going to use method 1 to simplify this. So notice there's not an equal sign, so we're not solving. We are just simplifying. So method 1 means that I combine the numerator into one expression if it's not already, which it is, or one fraction, I guess, and then the denominator. So for the denominator, I need to add those. My common denominator is going to be x times x plus 4. So in my first expression, I need to multiply top and bottom by x. And in my second one, I multiply top and bottom by x plus 4. So I will get x plus, I'm going to distribute as I go, 2x plus 8. Now I'm just going to rewrite my top fraction. And then here I will get 3x plus 8. Over x times x plus 4. I'm going to leave my denominator factored, as we've gotten used to doing. So now I have one fraction divided by another, so this is where we can do the keep, change, flip method. So we'll keep the first expression, 5 over x plus 4. We'll change the problem to multiplication, and then flip that bottom fraction. Then we're going to divide out any numerator with any denominator. So we can divide out our x plus 4s. Finally, multiply straight across, so we'll get 5x over 3x plus 8. So again, that's method 1, where you do the math so that you have one fraction divided by another fraction, and then you keep, change, flip, and simplify. So look at problem 10. X over 6 minus x over 3, all divided by x over 5 minus 7/10. I'm going to use method 1 again, just so you can see that, because these are fairly simple fractions to combine. I'm going to get a common denominator. Let's see, I think I'll write it this way just to conserve space, of 6. So up top, I have to multiply my first expression by nothing, actually. So that ends up being an x. Here we go. And then my second one by 2. So minus 2x. I'll simplify that in a minute. In my denominator, I will use a common denominator of 10. And then I have to multiply here, top and bottom, by 2. So this will be 2x minus 7. And I'll just make a note that I'm multiplying by 2 there. All right. Now I'm going to simplify my top fraction, so that'll be negative x over 6, all divided by 2x minus 7 divided by 10. So now we've got it in one fraction divided by another, so we can keep the first expression, change to multiplication, and flip. We'll divide out 2 from this top and bottom, and then multiply straight across. So we'll get negative 5x over 3 times 2x minus 7. And you can just keep your denominator factored, because there's no need to multiply that out. On the next problem, I want to show you method 2. Method 2, we find a common denominator between all the terms in the fraction. So write that problem down. You might want to pause because I'm going to go forward. And then any whole numbers I just put over 1 to remind myself that we can think of them in fraction form. So common denominator is x. That's my least common denominator. Now the method goes is that you multiply each term in this fraction. So in the numerator, the term on the left times the least common denominator over 1. And then the term on the right, so they all get multiplied by x over 1. Now at first this seems very cumbersome, but look what happens in this next step. So x times 2 over x simplifies to 2. 4 over 1 times x over 1 just simplifies to 4x. In the denominator, x times 2 over x simplifies to 2, and then 3 times x is 3x. Now the only thing left to do is to factor the numerator, but if you're looking ahead, you can see that's not going to help us simplify. But we'll go ahead and factor that numerator. And that's all we can do. Now this last expression, we're going to use that same method too. So finding a least common denominator. So I look at all my denominators, x plus 3, x minus 3, and x plus 5. My least common denominator needs to have both of those terms. So it will be x plus 5 times x minus 3. All right. So I'm going to multiply each of the expressions by that common denominator over 1. Now I'm going to write it 3 times because then I can treat each problem separately and cross things out. So x minus 3. As you get going on this method, you don't have to write it each time. Alright, in our numerator, you can see that 3 over x plus 5 times x plus 5 times x minus 3, these will divide out, and you'll be left with 3 times x minus 3. In the denominator, we can divide out x minus 3, and we'll be left with 2 times x plus 5 plus, divide out our x plus 5's, x minus 3. Now the only thing left to do is a little cleanup work. I am not as of yet going to multiply my numerator together. I'm going to leave it factored. I do need to go ahead and multiply and combine my denominator and see what I get. So 3 over x minus 3, and then I get 3x plus 7. I can't do any more factoring, and so I don't need to multiply that numerator. I can leave it as is. So that's how we simplify complex fractions using method 2, or least common denominator, or method 1, which is combining to one fraction in top and bottom and then keep, change, flip. This last problem is number 48 in section 7.4 in the book on page 389, in case you wanted to look at it. So you participate in a sprint triathlon that involves swimming, bicycling, and running. The table shows the distances in miles and your average speed for each portion of the race. So our first task is to write a model in simplified form for the total time in hours that it takes to complete the race. Well, the first thing you need to remember is just a simple formula that distance equals rate times time. But we want a model for time. So if we solve for time, then we can see that time is the rational expression distance divided by rate. So we need to total up all of those distance divided by rate, which is the speed for the swimming, the bicycling, and the running. So swimming, we have 0.5 divided by R. Bicycling, we have 22 divided by 15R. And then running, we have 6 divided by R plus 5. Now in simplified form, of course, so they want us to combine that. So I'm going to create a common denominator of, I need R and a 15 and R plus 5. So now I'm going to adjust each numerator. So 0.5 I need to multiply by 15 and by R plus 5. 22 I need to just multiply by R plus 5. And then 6 I need to multiply by 15R. So let's see if I can squeeze that in there. 15R. Did it. Alright, why don't you pause the video and simplify that and then come back and check your work. So once you simplify that, you'll get 119.5R plus 147.5 all over that common denominator. So that satisfies A simplified form for the total time. Now I've gone ahead and done B as well. So it says, how long does it take to complete the race if you can swim at an average speed of 2 miles per hour? Well, speed's in terms of hours, so we can just plug in 2 for T into our simplified expression, and you'll get approximately 1.84. Or, if you take the 0.84 times 60, that's 1 hour and 50 minutes. So that completes the notes for this section. Your homework assignment is on the backboard and also on the website. Good luck, and we'll discuss any questions that you have tomorrow.